Bismillahirrahmanirrahim. Assalamu alaikum everyone. So more and more digital logic design. So today we will be having our 8th lecture and we will be discussing more Karnaugh maps in don't care conditions. Though this is against our philosophy that in our society we do care. So let's start, right? So these are the points which we will be covering in today's lecture. Karnaugh map with 4 inputs, right? And the understanding of implicants, prime implicants and essential prime implicants, and how we can utilize those 3 categories of implicants, right, when we are performing simplification, right? And then how we can use don't care conditions while we are performing simplification by using K-maps, right? And in today's lecture we will be finishing the K-maps, right? So let's start. So whenever we have 4 variables and we have to map a Boolean function that has 4 variables by using K-map, right? So you can see that we have a table here, or you can say, or 16 different boxes at different positions that are interconnected. So how we place them, you can see M0, M1, right? If you consider those boxes, right, as Legos, so you can connect them but in a very different pattern, right? So M0, M1, and from here you jump here, right? So we have M2, M3, right? And then M4, right? So we move from here to here, M5, right? And then we will jump again, M6, M7, right? So from here, from this row, we will again made another jump, right? So M7, M8, right? M9, and then M10, M11, M12, 13, and 14, 15, right? If you look at the variables, so if we have 4 variables, so we name them W, X, Y, Z. So we place Wx, right, in this vertical direction, okay, and we have placed Yz in this horizontal direction, right? So you can see that we have the gray sequence, right, 0, 0, 0, 1, and that's why we jumped from here to here, because after 0, 1 we have 1, 0 if you want to follow the order, right? And then after 1, 0 we have 1, 1. So that's why we move from here, or we jump from here to here, and then we move from this column to the 3rd column, right? So if you follow this, right, 0, 0, 0, 1, 1, 1, 1, 0, same gray sequence, right, gray code sequence. And another thing that is very important over here, and I want to mention, you can look at those brackets, right? So if you look in this quad, right, this is the quad having 8 adjacent boxes, right? 1, 2, 3, 4, 5, 6, 7, 8, 8 adjacent boxes that are interconnected, right? So you can see that if we have the ones in the corresponding position of all those boxes, we will be having Y, right? We are left with only one literal, that is Y. And if we take this quad, you are left with X only, right? And similarly, if we have a middle quad, we are left with Z, right? And if you have the quad at the bottom, right, so we will be having W, right? So this is the simplification, if you have all ones in this quad at the bottom, you will be having a W only, right? So let's have the graphical interpretation of 4-variable K-map. You can see that we have a Boolean function over here, and we can represent this as the summation of min terms. So these are the min terms, right? So you can see that if we consider this quad, right, so this will interpret graphically this upper vertices, right, portion, right? And if you talk about this pair, then you can see that we have to join those two vertices, right? And if you have the number of ones at all 4 corners, right, of this square, or if look like a rectangle, right, so we will be having this physical interpretation or representation. So you can have an idea that how those different pairs, squares, quads, they can be think about, or they can be interpreted graphically, right? So here let's talk about some simplification, right? So if you look at this middle table, right, so you can see that we have ones at the diagonal, right? So if you want to make a pair, so we can only have the pair, right, horizontally or vertically, or we can have pairs by swapping or bending, right? So here we cannot do that, right? If I bend, this one will go here and we don't have the pair, right? And if I flip, right, this, right, while considering the vertical column, right, so this one will move here, right? So we again will not be having any pair, right? Remember that we can only bend or flip one time, right? So if I am allowed to flip twice, so when I will flip those columns, I will be having that one here, and then when I will flip horizontally, so then I will be having the pair, but that is not allowed. So the conclusion is that if we look at this representation, this K-map representation, we will not be having any simplification, right? So it is useless to map the Boolean function when we have a representation like this, right? But you have to verify. So here we have no simplification, right? So if we represent it by using simple Boolean algebra representation, or we can use K-map, right, we will be having no more simplification, right? So, and if you look at here, look at this K-map representation, so you can see that there is so LT less than or GT greater than. So maybe we will be having more simplification, or we will be having less simplification, or we will be having more number of gates that are being required for the representation of this Boolean expression, right, represented by this K-map, or maybe we need greater number of gates, right, or we will be having greater simplification. So that's a sort of homework for you people, so you have to look, but I just explained over here that you can have even no simplification even by using K-map. So here you can see that we have a representation that includes ones at the diagonal, right? So we are left with no simplification, right? So you can see that this is the K-map for LT, right? So this will make no difference, right? So you equal, right? And then we will be having, right, greater terms, right? Okay, so can we draw a truth table for these examples? So let's have, or we can try, at least try, give a try, right? So we have the 4 variables, right? So if I plot, so we can at least give it a try, right? So we have the 4 variables, right? Right. So what we can have, we can split this like this, right? So here we have A, B, and here we have C, D, right? So we will be having 0, 0, right? 0, 1, and then we will switch over here. So we will be having 1, 0, 1, 1, right? So if I have to write here, so A bar, B bar, right? And then A bar, I will replace A bar whenever I will see 0. So here we have A, B because both ones, and here we have A, B bar, right? Okay, so again here when I will be moving, right? 0, 0, right? 0, 1, right? So and then 1, 0, and then 1, 1, right? So if I have to C bar, D bar, C bar, D, right? And then we have C, D, right? D bar, right? So right, so what I can have, so I will be having a 1 over here, right? So it means that will correspond to A bar, B bar, right? And then we have C bar, D, right? Okay, and I have a 1 here, right? So I will be having A bar, B bar, because this is the column, right? And this is the row, so I will be looking at this row, so I will be having C, D, right? So if you look here, we have a 1 here, right? Here, here. So what we will be having, right, A bar, B, right, and CB. So here what we will be having, A, B bar, right, and CD, right. So similarly we will be having A bar, B bar, and CD bar. Okay, A bar, B, this column, and CD bar, right. So we have 1, 2, 3, 4, 5, 6 different expressions. So if you start from m naught, right, min terms, and this is m1, right, and then we make a jump, m2, m3, right, and here we have m4, right, m5, right, and then we will be having m6, m7. So remember, here we have to jump here, right, so m8, right, m9, m10, and m11, right, and then we will fill this, right, m12, m13, m14, and m15, right. So these are the corresponding, right. So here, if I want to have truth table, right, so what I can do, I can start from 0, 0, 0, right, and then I will be having 0, 0, 1, 0, 1, right, 0, 0, 1, 0, right, 0, 0, 1, 1, right, so 0, 1, 0, 0, right, and then 1, 0, 1, right, this is 0, then 1, 1, 0, this is 0, right, and then 1, 1, 1, oh sorry, 1, and then I will be having 1, 0, 0, 0, right, 1, 0, 0, 1, 1, 0, right, 1, 1, right. So these are the repetitions, right. So here I will be having 1, 0, 0, right, 1, so 1, 0, 1, 1, 1, 1, 0, right, 1, 1, 1, 1, right. So what I will be doing, m0, m1, m2, m3, right, m4, m5, m6, right. So I will move on, m8, right, m9, m10, m11, m12, and we will finish with m15, right. So I started from 0. So you can see that we have a 1 here, right. So we have a 1 here. So this is m4. So what we can do, if I have a function f over here, so I will place a 1 here, and then we have, right, we have m8. So here we have the m8, right. So I will place a 1 here, then we have m9, 1 here, right, and then we have m14. So m14 is here, right. So this is the way out how you can always construct the truth table directly. So for your understanding, I have started from the K-map, so you can always have this sort of K-map representation, right. So we can draw the truth table if we have the K-map, right. So then whenever you talk about design, digital design, so ultimately our goal is to build a practical circuit. So there are certain steps we normally follow or adopt whenever we talk about physical implementation, right. So we start from the truth table because we have to start from somewhere. We need something, we need Boolean expression. So if we keep in mind, if we focus on K-map, so we have to start from the truth table, right. So we have, if we have the truth table, right, right? If you have this sort of representation, so from here, right, this is the truth table, you can always map those min terms over this K map, right, Karnaugh map, right? And then what normally we do, we perform the simplification so that we will be having a simplified circuit that can perform the similar job, right? And then finally, after the simplification, we will be implementing the circuitry or simplified Boolean expression by using different gates. We will be using AND or NOT, right? So you can see that over here that we have the corresponding physical representation, right? So here we have the NOT representation, here we are performing AND operation, and here we have adding them, we are performing addition operation, right? So finally we will be having the physical implementation that is performing the same job, right? Okay, so let's have another K-map with 4 variables. So you can see we have a K-map, right? So this is the way out how you group those ones, right? So you can see that we have different groupings, right, over here, and different squares and different grouping of ones in column, and then finally we are left with this Boolean expression after the simplification. So there are some tips which we normally should follow, right? We have to make sure that all ones are being used properly, right? And then what we need to do for more simplification, right? So we must minimize the total product terms, right? So here if you look at this expression, we have more product terms, but over here we have less number of product terms, right? And then the design, from the design point of view, you can use NAND gates or NOR gates, and you can use OR and NOT, it's your choice, right? But NAND and NOR, they are universal gates, and they have some good characteristics which favor us for the digital design. So that's why we try to implement the final Boolean expression by using NANDs and NORs, right? And now let's move to another important topic, that is don't care. Although we do care in our normal life, but this is a technical terminology. So how we can exploit or use don't care conditions to have more simplification when we are using K-maps, right? So let me give you an example. So let's say you have a two control or two level, right? Or you can say you have two switches, right? Interlocked switches, and there is a scenario like you can close one switch at a time, right? So if you close one switch, you cannot close the other switch, or in other words, you cannot close them simultaneously, right? So what sort of possible combinations we can have with all? So first we will be having both of the two switches, or both are open, right? So we can represent them 0, 0. So if one of the switches is closed, so we can say that 0, 1, right? And then if the other switch is closed, so we can represent that scenario with that situation with 1, 0. So as I have mentioned that both of the two switches, they cannot be closed simultaneously, so it means the 1, 1 combination cannot happen, right? So this has to be ensured that 1-1 combination will not occur. So that's scenario where we can declare 1-1 as a don't care, right? So, and then we can use that 1-1 combination accordingly if we feel that it can benefit us from the simplification point of view. We will consider it as we want, right? And we normally place an X, or maybe sometime you will see D written whenever we have a don't care condition. So this is the scenario where you can think about what a don't care condition is all about, right? So let's move to the K-map with don't care conditions, right? So as I have mentioned that we will be having don't care, right, when the output or the combination is guaranteed that it will not happen, or it will not, right? So as an example, you can say that if we have two switches, interlocked switches, so those two switches, they cannot be closed simultaneously. So if we replace the closing of a switch by 1, so at a time one switch can be turned on, the other has to remain off, right? So we can say 0, 0 if they are both open, 0, 1 if one of the switches closed, and then we have 1, 0 if the other switch which was open previously, it is closed now, and we have a 0, that switch is open, right? And as the switches cannot be closed simultaneously, so we cannot have 1, 1, and it has to be ensured, right? So this is the way out how you normally represent don't care conditions. We have ones, right? Okay, and the don't care conditions are being represented by X, right? And in literature sometime you will come across D, and that also represent a don't care conditions. So we can use those don't care conditions accordingly. So here you can see that we have an X over here, right? So we can consider it a 1 because it will simplify our Boolean expression, right? And you can see that we have those 4 ones, right? So you can always consider that don't care or use that don't care position accordingly, right? So this is the same stuff, right? Like some tips regarding the don't care conditions, right? You can use the don't care conditions according to your design, right? If it can assist you in simplification when you are replacing it 1, you can do that, or you can take it as 0, right? If it is not helping us in helping you in simplification, right? So here are more examples, right? So you can see that we have used don't care conditions. We have 1 here, right? And 1 here, okay? And then we have 3 ones here, right? So we can use don't care conditions. So this is one way of using don't cares, right? You can see that we have B if we consider this quad, right? And we have AC, right? If we consider this square, right? And by having this pair, we are having A bar, C bar, D. So this is one representation. You can also, so this is the same representation, right? You can also have this pair, this square, right, and this square, and then we are left with this one, right. So it's you can see the difference, right. So this is a one way of minimization. You paired them, or you look for squares, right. So this is also a square and this is also a square, right. So you can see that we can have simplification. So this expression is more simplified expression, right. Then more examples, right. So here we can represent the Boolean expressions of before. We only have minterms, and now we will be having don't care conditions, right. So we will write a D and we will place the minterms. So here we have minterms that will represent actual ones, and these are the don't care conditions that will be replaced by X, right. So here you can see that we have 1, right, 3, 5, 7, 9, right. Right. So this is a sort of representation that how you can. So this is the simplification without don't care, right. And this is the simplification with don't care. Now we have used this don't care and we consider this X as 1. So you can see we have this care. If we don't have this don't care, or we will not use this don't care, we will be having a much more complicated expression, but by using the don't care we have simplified expression, right. Okay, so as I have mentioned that some don't care you group and some other you don't group. So here you can see that this don't care is grouped with this one to have simplification, and this don't care have not been utilized. So it means we are placing a 0 here, right. So it's up to you. So as I have mentioned that some don't care you group and some other you don't use. So over here you have grouped this one with this don't care condition and you got this simplification, and when you use this, you take this X, you have not used it, you have not grouped this with, right, any other box, right, because we have 0, so we have taken this X as 0, right. So then we move to the implicants and prime implicants and essential prime implicants, right. So as in the last lecture we touched those technical terms and we try to differentiate between an implicant, then a prime implicant, and then the essential prime implicant. So the prime objective, the major objective is to exploit those prime implicants, right, or those implicants, prime implicants and essential prime implicants sort of representations to have more simplified Boolean expressions, right. So let's have more example, right. So here you can see that we have different grouping, right, and we also have the don't care conditions over here. So you can see that these are the 6 prime implicants, right. Right. So if you look at the simplification, so the expression that cannot be further simplified, we can declare it a prime implicant, right. So whenever we have a grouping, right, so you see that the ultimate goal is to eliminate a literal, right, or a variable, right. So over here you can see that we have 6 prime implicants and they cannot be simplified anymore, right. So within those prime implicants, we will be looking for essential prime implicants, right? So you can see that this AC, B, C bar, A bar, B bar, D bar. So if you look at AC, so we have A, right? And this is the C. So this is AC, right? So you can see this prime implicant, because whenever we are grouping those ones, right, that are in this square, our ultimate goal or ultimate objective is to have a simplified expression, right? So you can see, if you look within this square, so the ones, they have the minimum cover. So here this one has been utilized, reutilized, you can say, right? And then those two ones, they are also being utilized, reutilized, right? But this one has not been utilized, so this has the minimum cover, right? And then if we look at the BC bar, so you can see it will also have the minimum cover. So this is the philosophy of prime implicants and essential prime implicants, right? So you can have another example, right? So over here we have 5 prime implicants, right? So you will see that we have 1, 2, 3, 4, 5 different pairing, right? So here we have a square, we have paired those or combined or grouped those ones in a square, and we have combined those ones, right? Those ones, right? And then we have another grouping. So if you count 1, 2, 3, 4, and 5, right? So these are the 5 prime implicants. And again, let me mention, or let me point out that our ultimate goal is to eliminate a variable whenever we are grouping those two ones, or we are having this square, or grouping those two ones or those two ones, right? So within those prime implicants, we can have essential prime implicants, right? So if you look at A, B, C bar, right? So you can search and you can look which of them are essential implicants, right? So the ones that have not been fully covered, that have the minimum cover, right? So we have the 4 essential implicants, right? So this is the definition, right? So you can see we have prime implicants and implicants, right? So you can see that we have A, C, D, E, A, C, D, E. They are the implicants, right? Because we can have groupings, right? So this is another example, right? So you can see that we must have, right, minimum sum of the products forms, right? So let's have the graphical interpretation or representation of prime implicants. So you can see that we have different groupings, right? So where we will be having the essential prime implicants. So you can see that if you consider this one, because we have flipped first, you can say horizontally and then vertically, and then we have this square that includes the ones at the corner of this table, right? So but if you look, right, so this one has been reutilized when we have this in this, right? and this one has also been utilized when we will be having this for one grouping, right? But this has not been utilized, so this is minimum cover. So we can say that, or we can declare this as essential prime implicant, right? And then if you look at this square, right, at the center of this table, so you can see that this one has been reutilized, this has been also reutilized, this also has been reutilized, but we have not utilized this one again, right? So this have a minimum cover, so we can say that this is also an essential prime implicant, right? So BD and B bar D bar, right? So another example, right? So you can see that we have here 0, 2, and 3, 8, 9, 10, 11, 12, 13, 14, 15, right? 0, right? So then we have 1, right? 2, right? So 0, 2, 3, and then 8, right? So 4, 5, 6, 7, and 8, right? 9, 10, 11, 12, 13, 14, 15. So these are the min terms, and this is the Boolean expression, and we have K-map representation of this Boolean expression, right? So you can see that we have a quad at the bottom, right? And then we have a square, right? If we flip horizontally, so we can have a square with these two ones and these two ones, right? We can bend or flip horizontally, right? And then if you bend or flip horizontally and then vertically, then we will be having those corners, right? And those corners will be a square, right? So you can see that we have prime implicants, right? If you consider this quad, we will get A, right? Right? And if you look at the squares, we will be getting, right? Because we got this square, right? And square with the ones at the corners, right? So we will get 2 more terms, and those are the prime implicants, right? So you can see that this one is not utilized, right? If you consider this square, right, that includes ones at the corners, and if you consider this square, this one has not been reutilized, right? And all those ones, they are not utilized, right? So all the prime implicants, they are essential, right? So this is the example that has been taken from your book, right? So you can see that we have a Boolean expression. So here we have the min terms, right? And here we have the don't care conditions, right? So you can see that we can have, so first we will be plotting ones, right? So 1, then 3, and then we have 11, right? And then we have 15, right? So if you have to mention the don't cares as 0, and then 2, right? And then 5. So you can see that we can have this horizontal line by grouping, and then we can have this vertical column again by grouping those ones, right? So you can have yz plus w bar x bar. So we can have w bar X bar, right, and YZ, right. So here you can see that we have utilized another grouping, right. So what we did, we have used this don't care, because we have always choice. We can use this don't care. So as you can see here, we have used this don't care and this don't care, but we can always use right, or we can not use the don't care, right. It's your choice. So here you can see that we have used this don't care, right, and we grouped, or we have this care, right, and then we have this column. So you can see that we will be having the same expression, right. So here we have you can say YZ, right, and here we have W bar Z. So you can see that we have used don't cares differently and we have the same expression, right. So this is another scenario, right. So again, don't cares. So you can see we can use or we cannot use. So it's all your choice, right. Whenever you feel that you will be having more simplification, right, so you can use the don't care positions or boxes accordingly, right. So let's talk about implicants, prime implicants by having don't care conditions. So here we have a Boolean expression that includes don't care conditions, right. So you can see that we are building different groupings. Like here we have a group of 4, right, and we have grouped those 2 don't cares, right. So you can see this is an essential, right. Why? You must have an idea that why this is an essential prime implicant, right, and this is also an essential prime implicant, right, and because this one is not reutilized and over here this one is not reutilized, right. So here we have an example where we have ones and don't care conditions, and we are naming them as prime implicants or essential prime implicants, right. So this is another representation, another way out. So I don't want to have a confusion, but normal we have different books from different authors, and there is a sequence, right, and there is mindset associated with those different writers. So I come across this representation, so I thought maybe if you come across that sort of K-map representation, so at least you should know, although we will be following the textbook and we will be following the notations, the representations that are available in our textbook. But being a student, you should always know that you can also do that, or you can also have this sort of representation. So let's have an example, right. So you can see that we have 2 different implementations of Boolean expression. So we have a Boolean expression. So this is these are the min terms and these are the don't care conditions. So here you can see the difference over here is that we have 2, right, 4, 5, 6 and 10, right, and don't cares we have 12, 13, 14, 15. So instead of moving, right, or starting from the rows, this author or in this book it starts from the columns, right. So you can see that we have 0 here, so we can name it, right, or we can write. So if I have to write, right, so I will write m naught, right, because I will be moving m1, right, and then this is m2, this is m3, right. So I will move here, right, m4, right, and this is m5, right, and this is m6, and this is m7. So these are the min terms. So as we have to follow the gray code sequence, so you can see that here I have jumped from this position to this position, right. So here and again I have to jump from this column to this column. So here I will be writing m8, m9, right, and here m10, right, m11, right, m12, right, m13, m14, and m15. So this is another representation. So you can see that we have 2, right, so we have a 1 here, 4, we have a 1 here, 5, we have a 1 here, 6, where is 6, so we have a 1 here, right, and then after 6 we have a 1 at 10, so this is 1, right. And when we are mapping those don't care conditions, so you can see D, M12, M13, 14 here, so we have don't care conditions over here. So this is another representation, but we will be following the representation that is being used in our textbook, but you should at least know that we can also have this sort of representation. So you can see that this is the simplification, and you can have this care, right. We have used those don't cares, and we can have a grouping at the bottom, right. So we have this, so this will be x2, x3, and so this is the sum of the product terms, right. And when this all, you know that if we want to complement this, right, so what we have to the remaining zeros, right. So we have if we bend or flip vertically, so we have a square here, right, and we have the 4 zeros and don't care position. So here you can see that we have used this don't care by replacing 0. So we have x bar plus x4 bar, right, x3 bar plus x4 bar, right, and by with this map grouping you will have x2 plus x3. So this is the product of sums, right. So this is the example, and you can try it yourself, right. So again this is the Boolean expression, right. So what normally we can do, we can so you always can start from the simple one, and then you can, as you practice more and more, then you will see that your problem solving time is being reducing. So here, if you are a beginner, so what you can do, so here we are missing, because you can straight away judge that this is a Boolean function with 4 variables. So here we have B, C, D, and we don't have A. So what you can do, you can multiply this with, right, so you can multiply this B bar, C bar, D bar with A, right, plus A bar. So because this is always 1, right, So here we have all 4 variables, right? So we will write it as it is, right? And here we again don't have B, C bar, D, and we will be multiplying A plus A bar, right? So, and again here we have all the, right? So this is the simplest way to start. So now you can have A, B bar, C bar and D bar, right? And then A bar, B bar, C bar and D bar, right? And then we have A, B bar, C, D bar, and now we have A, B, C, D bar also. So we don't have bar here, we have actually bar. So let me C bar and D, right? And we have A bar, right? B, C bar and D, and finally we have A bar, B and C, D bar, C, D, right? So now what you can have, right? The goal is to map it here, right? So this is, although this is a lengthy process, but if you practice more and more, you can straight away map those different expressions, right? So here what you have, you can see that we have 1, 2, 3, 4, 5, 6, right? So 1, 2, 3, 4, 5, 6, right? Right? So you can see that where we have so A bar, B bar, C bar, right? So this is done, right? Then A, B bar, right? So we will be looking for A, B bar here, right? And then C bar, D bar, right? So A bar, B, right? So A, B bar is here, right? And then C bar, D bar, right? So this is done, right? And then we will be looking for A, B bar, right? A, B bar, C, D bar, right? A, B bar, C, D bar, right? So this is also done, right? And then we have A, B, and C bar, D, right? C bar, D. This is also done. And A bar, B, right? So A bar, B and C bar, D, right? A bar, B and C bar, D, right? So this is also done, right? And A bar, B, C, D. So A bar, B, C, D, okay. So that's over. So you have mapped all the ones, right? All the min terms, right? So, or what you can do, there is another method, but again it's up to you that if you want to follow a very lengthy process, or if you have enough experience or practice, you can straight away map this, right? So then after that you will be looking for groupings. So you can see that we have, after banding, we have this pair, right? And this is the pair without banding, right? Then we have this pair in the second column, so we will be having a simplified form, right? So this is the sum of the products, right? And then if you wish to have the complement, right? The complement of this, right? So what you will be doing actually, so we will be looking for the positions that are left, right? So we don't have a 1 here, so we will place zeros over there, right? So you can see that we left all the ones and we placed all we filled rest of the positions with zeros, right? So here you can see that we can pair, right, those zeros, right, and we will be having the complemented Boolean expression or Boolean function, right? So that's all for today's lecture, right? So it's almost the end of K-maps, right? So we have K-map with 4 variables, right, today, and then K-map mapping with don't care conditions. How can we achieve more simplifications or more simplified sort of Boolean expression if we are using the don't care conditions, right? And then we have used literals, right? Implicants, prime implicants, and essential prime implicants, right? And we have utilized those concepts when we are simplifying our Boolean expressions. So that's all for today's lecture. So अपने दोस्तों का, अपने रिश्तेदारों का ख्याल रखिएगा. अल्लाह हाफिज़. अस्सलाम वालेकुम.